Okay, very good. All right. So, are there any questions or issues that people want to bring up? Anything? Just type them in the chat if you wish. All right. All right. So today we're going to cover normalization theory, and I'm going to start out with this brief presentation that's supposed to give you some kind of intuition and motivation to why this is important. So we'll start out with that, and then I'll just kind of go through maybe doing a lot of trying to work with a lot of problems, because this is kind of it's one of those things where you get more intuition as you kind of work with it. So okay, so just a little bit of background knowledge, and I'm assuming that we all know this should be pretty clear to everybody. We have the kind of notion of a relation, which is like a table, but we call it relation for these purposes. And then they have attributes, of course. So that's the kind of the main headings of the table, or the attributes of the relation. In this case, what we have a person ID, we have a name, a street, a city, and a postal code. And then we have a database instance. This right here is the database instance. This is one of potentially infinite numbers of different databases, states, or database state or database instance of this particular relation. Now, there's what's called a functional dependency. So normalization theory is based on what are called functional dependencies. And what functional dependencies do is they're of the form, essentially, X is a set of attributes, and then right arrow Y as another set of attributes. So in this case, the set X is just the set PI, including PID, and Y is the set including name, street, and city. So as you see, these are attributes up here. And so what does this mean? What does it PID implies, or PID functionally determines? So when you see this arrow here, you can read that as determines or functionally determines. So a PID determines a name, city, street, street, city. So what that means is it means if for any database state, if two tuples match on PID, then they're going to match on the name, street, and city attributes as well. So it's a little bit more interesting when we look at this one right here, because what this says, right, this is kind of like your natural kind of notion of a primary key, it feels like. Because sure, if two tuples match on the PID, but no two tuples are going to match on the PID. There's only going to be one of them, right? So therefore, of course, once you know this, then you should be able to determine a unique name, street, and city. But this is actually kind of showing a little bit more of the power, or a little bit more of the flexibility of this way of specifying things via functional dependencies. This is not a primary key. But any two tuples in this database here, any two tuples that match, that have the same street city combination, and there are two tuples here. There's this tuple 21, tuple 22. They both have Cirkelwagen 14 as the street address and Stockholm as the city, right? So they both match here. And then what that means, it means that they have to match then also on P code. So any tuple that has any two tuples that have the same values for these, the street and city, have to have the same value for the postal code, okay? And they do. In this case, we have, they both match on that code. Now, if this was instead, right here, if this was, let's say make that a 4, then that's violating this functional dependency. Because what that means is so this functional dependency is not being observed over this database state here. I hope people see that. Because if they both match, they both are going to match on the street and city, but they're not matching on P code. So given a particular street and city, you do not know a particular P code. You cannot determine a particular P code. Okay? All right. So yeah, so terms, relation, the whole thing, attribute, tuple, this is 3 tuples there, a key. We'll get to keys more throughout. And then the notion of integrity. So integrity means this. It means that if I make these statements here, these functional dependency statements, then I'm making a statement about, there's an infinite number of potential database states here. But when I make a statement like this, I'm basically saying that, well, let's only consider the subset of the infinite subset of that infinite set of states where this is being respected. Okay. So what that's allowing us to do is to specify some kind of integrity to the database that it should not violate, right? And then we can make sure that the mechanism of the database ensures that this is going to be observed. Okay. All right. So that's that should be hopefully pretty straightforward. All right, so now let's consider this. This is a little bit more broader example than the example that I had before. It has an account, a bank account number, and then a balance for the account, a person number who owns the account, the name, the street, the city, and the postal code of that well, we have the person, and they live at that postal code there. All right then. So this is what's called a universal relation, because it's one big table. So a lot of times what you'll see, this is maybe not as true as it used to be, but sometimes you'll see it, that what an organization will do is they will simply say, well, we want to define a database, and then somebody thinks of what are all the attributes of the database, and let's just make one giant table to kind of encompass everything, right? So this would be an example here. We want to have people with accounts, and we want to have them living in places, and we want to have so they can have multiple accounts and different balances in those accounts. So that's how we're going to design our database. So this is consider this to be a candidate design for a database for the bank. All right, we're going to see that would be not a very good design, and we're going to have some good principled ways to say why this would be a very bad design for the bank. Anyways, though, if we look at it though, we have the following functional dependencies that are being observed here. We have an account number determines a person who owns the account and an amount. Okay, so in this particular database here, we don't have joint accounts. We could deal with joint accounts. We can model that, but this is not what we're modeling here. So the theory is able to kind of it's the interesting thing about the theory is in the theory we will actually be able to specify things like being able to have joint accounts. But one thing we definitely want to have is we definitely want to have account determining an amount in the account. All right. That seems like it would be a natural thing to have. Although you might say, well, that's not really true either. But we'll get to that. We'll get to maybe some of these more complicated examples. Because actually, it's the account at a particular time that would determine how much money is in the account, and that we think maybe should be respected, right? Because at any particular time, we should be given an account number and given a time value. We should be able to determine how much money is in the account. But we're doing a more simple example here, where we're just basically saying like this is like a snapshot database. There's no time involved. We're doing one where we're basically saying the account will determine who owns it and then how much money is in the account. Now, the person number given a particular person number or the person number, that will then determine a name, right? So the person number 20, okay, that determines Mike. Oh, and there's another one here, but they both determine Mike. If this was a different name here, Mike R or something, then that would be a violation of this functional dependency. Person ID also determines the street. So people can only, in this example here, can only live at one address. Finally, we have this right here. This is one we've seen before. The street and city determine the postal code, and that is true in Sweden, and I think in many places. Well, it makes a lot of sense because we have the street address here. In fact, it may very well be that the street. Well, we'll come to some questions about this later. I was going to ask. It may very well be that the street determines P code. Let's think about that for a second. Just kind of like just to make sure everybody's kind of on the same page here. So, so I hope people can see this. Street determines P code. Now this is a database right here that only contains 3 tuples. Is this true, by the way? Is this true in Sweden? Exactly. Yeah. So I think that there's a street named what's a street that is Skolgatan kanske? Eller finns en street Kungsgatten kanske. Kungsgatten, there's a Kungsgatten in Umeå, right? Is there? Strand. Yeah, good. Okay, there we are. So, so there might be something like the street address Kungsgatten 10, and that does not functionally determine the postal code, right? Because there's going to be a different postal code from the one in Stockholm from the one in Umeå, right? So this is definitely not a valid functional dependency, right? But you can kind of play around with this. Now you might say something like, well, it happens to be in Sweden that that let's say we look around and we find out, well, it actually happens to be observed happens to be observed in Sweden for some reason. It's not, but still, I mean, in principle, you should avoid it because it doesn't. It's kind of like saying first name, last name functionally determines the grade. But that's not true, but it's almost always true. But sometimes you get two students with the same first and last name. It'll happen. So it's best to kind of model your database so you don't have, you don't use the first and last name as the key, right? That would be, because it's not truly a functional dependency of the database. Okay, anyways, this is kind of showing how some kind of, you somehow discuss these design issues as you're kind of coming up with these things. But anyways, these three functional dependencies do seem to hold, or we're going to model it so that these three functional dependencies hold. Okay, so now what we have here is we have what are called update anomalies. So the problem with making things in this giant table here is it's going to lead to potential problems, anomalies, in the case of the update. So right here, let's say that I update the address for Mike here to this address in Stockholm, and I do it for this tuple, but I forget to do it for that tuple. Okay, I forget to do it for the second tuple. That's a problem because now we have an inconsistency in the database. We have an anomaly. What address does Mike actually have now? Which one? Which one is valid? If you ask the question, what is the address of Mike here? It'll come back and say, well, it'll return two addresses. And based on the way we wanted to model our domain here, model our database, we don't want that. We want to have people to have unique addresses. So we already have a problem here. So the thing is, if we are going to make changes to the address for Mike, we're going to have to now have a protocol, or we're going to make changes for all the addresses of Mike. Okay, so you could probably do that in a simple case, but it's starting to kind of make it so that we have more complicated protocols over updating the database. Okay, so it's kind of a little bit, it's not the best thing, but you know, maybe we can kind of have routines on the client side that will, when you update an address, it goes through all the tuples and make sure they all get updated. Okay, that's a possibility. But you can see if somehow or another you don't fully kind of get, if you change the database schema then maybe, and then the client changes or something, you can see how maybe the database would get into some kind of sloppy doppy state. That's a technical term, sloppy doppy. It means just kind of everything's kind of, I mean, and this happens in the world, right? Is that somehow that database doesn't seem right, and that database is kind of flaky. Something's weird's going on there because we changed the address, and it keeps on popping back up again. Anyways, you know, the fact that, I mean, we've all had the experience of having our address changed many times, but the stupid system doesn't seem to be able to take it. But that's usually for a different reason. But it kind of gives you an idea that you're getting into kind of sloppy territory here if you're just having this giant big table. So we have this update anomaly. Now we also have some what are called insertion and deletion anomalies. So we did an update, but now we're going to do, what if we delete account 3? All right, so if we delete account 3, that was Sam's account. Sam lives at Kyrkogatan in Stockholm, you know, and then we want to delete the account number 3. Well, if we do that, if we delete the whole tuple, then we're going to lose also Sam's address information. All right. And so we just lost information. We you know, we could, I mean, maybe Sam is just, you know, he closed one account, but maybe he'll open it again. We don't want, or maybe, you know, he got angry at us one day and we want to keep him around so that maybe we can send him kind of a nice email or a nice letter later saying we're sorry that we made a mistake with the account or something. Because we want him back as a customer. But the thing is that if we're having this big table, we either going to delete the whole thing, or we're going to do something kind of really rinky-dink, and we're going to go and we're going to put null values in. Another potential use of null values is that, well, because we wanted to delete something. All right, well, it's getting junky, right? It's kind of, we're going to see there's a much cleaner way of doing all this. All right, finally now we have an insertion anomaly. Let's say we want to add Susie without giving her an account. So we just, Susie comes in. We know that Susie's going to later on get an account, but she doesn't have the money quite ready yet. So we want to take her persona number and her address in here. But now what do we do about this? It looks like we're going to have to make these nulls. Okay. All right. So, well, anyways, it's a little bit of a flaky database. So, all right. So we have this big table here, and now we've got because of all these kind of complexities and all that, we've really beefed up and made really, really nice our client programs. So our client programs that go in and make and do the SQL that maintain this, now they're really kind of advanced, right? They have lots of conditionality inside them. When they do inserts, they check over other stuff and then do the inserts over the whole database. Rather updates, I mean. And then inserts, what they do is, well, we handle them with null values, but now we have special code on our client side that interprets those null values. So we can do it, right? We can just kind of throw programming at the problem, but our database is sitting in the center there with kind of in a junky state or potentially junky state. And we have these complicated client programs on top of it. All right, so that's how we're dealing with it. So now, does that happen in the real world? Do people not do good database design and then have much more kind of complicated client programs? Yeah, that absolutely happens. Yes. So because and what are some other problems with that? Because like people would say, oh, I can make this work. Yeah. The thing is, if you have a really complicated client program that's doing this, and then you got version 1.01 of that, now you're going to go to 1.02 of that. And this thing does a little bit different. It's now you have this whole kind of jungle developing over here in terms of the clients. And now you got one old user who doesn't want to update their client, who's using the old version of the client. It's just, now you're really, wasting time. Okay, so, all right. Finally, let's look at this right here. Now we're going to add this. We're going to add in. So now here's our database state, and now we're going to add in Dave with an account number 2, and we're giving him 6,000 crowns, and we're going to put him at this address here with that postal code. Now the thing is that this is a bad tuple. This is we have to somehow maintain. We somehow have to reject this being added in, right? First of all, account number 2 is already taken by Mike, so Dave can't have it. He's got to have a different account. We got to give him account number 4, right? 20 also. What is this guy? He's just some kind of trying to take over Mike's persona number. No, we're going to give him his own persona number. And what's this right here? Look at. He's got himself working. He's got the wrong postcode here. What a dunce. So now we got to make sure that we get that right. So in other words, just because this thing, when it was added in, now we got all this work to do to go and make sure that he's not violating the functional dependencies that were supposed to be observed. Or we can just let people enter the data they want into the system and not do any checks. And then the database is really looking like junk, right? Because now those functional dependencies we had before are not even being respected. Now it's just, why not, you can just throw anything at the thing, right? So that would just be bad. All right. So this violated several functional dependencies, and then it would require expensive protocols to maintain integrity. But you could do it. You could go into your client program and you can make all the checks inside your client program, version 1.01 of the client program, and then maybe you have to kind of tinker with that for 1.02. I hope that everybody sees that this is leading to kind of a problem. I mean, unless it's a consulting company who's getting charged by the hour and the client is dumb enough to pay. Sorry. I mean, but it's still a problem. Unless we want to do a professional job. I mean, we should always want to be as direct as possible. Okay, isn't this? Yeah, the thing, okay, yeah, you would prevent it. Yeah, you would prevent this tuple here, you would prevent it from being, but you have to go and you have to check. You'll have to go and check. You have to have kind of checks inside your front end to make sure that you don't let this thing through. All right, it's going to be complicated checks. Yeah. So, I mean, so the thing is that wouldn't there be a nicer way? Because I mean, this is. I mean, if we wanted to spend time on doing something, we would do some. You know, we would like make a voice recognition interface to the thing or something. We would do something kind of more interesting rather than wasting time and effort on this kind of stuff. I mean, you could build up a giant kind of ecosystem of really nasty client code. In fact, I think there's whole industries that do that basically. Anyways, okay, you could do that. But the thing is that if you're in the process of designing your database, you don't want to go down that path. You want to do it better. So let's think about how we would do this. All right. So what if we decompose? What if, instead of having this big table, so instead of having this big table here with all these guys right here, what if we do this instead? We're going to have 3 different tables. All right. This is what we're going to do. We're going to, and that's called decomposing. So what we're doing is we're taking this table that has 1, 2, 3, 4, 5, 6, 7 attributes, and we're busting that into a decomposition of 3 tables or 3 relations that have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 attributes. Some of these attributes are repeated, though, of course. All right, so let's look at that right there. So now, so what if we decompose? Okay, so decompose. That's basically the theory is going to be giving us ways in which we do these, which we compute these decompositions. So the verb is to decompose, and the result is a decomposition. So we go from R into 1, 2, and 3 different relations. These are the 3 relations. All right. So if we look at this right here, let's consider this. Okay, is this a good decomposition? Is this a better way to do things? Is this a better way to do the database design? Well, let's see. Well, first of all, we have to know this. It's like, you remember, like, if you remember the whole business of, like, you know, you would, when you were a kid or whatever, you would, or maybe a little bit older than a kid, like, you know, adolescent or teenager or something, or even now, you know, there's some kind of complicated, you know, piece of machinery or something. You want to take it apart because you're interested in what's going on with it, or it's got a problem or something, you know, whatever. So you take it apart, you completely take it apart. That's decomposing. But then you got to put it back together again. And there was always the thing is when you put it back together, there's that one part missing, or there's one part left over. You don't know where it belongs, and you know you did a boo-boo. That was a lossy decomposition because you split it apart, but you can't put it back together. All right. So, likewise, if we decompose R into these 3 relations, the very first question to ask is, did we just lose information? I mean, if you just kind of willy-nilly decompose something, you know, you kind of bust it, you know, you break it apart, you may not be able to put it back together again. So let's see if we can put it back together again. So that's always the very first question. Is it basically lossless? So we want it to be lossless. Lossless means we don't lose anything. All right, so if we look at this right here, we have, this is R1, R2, and R3. And with this, because you remember the relational algebra, we can do operations like natural join. All right, so if I basically say this, I do a natural join of R1, R2, and R3 together. So the R prime is going to be this natural join with that. And what is that going to be? That means that we're going to do the join on the PID here, right? So that actually equals this. And then we're going to do a join of this right here on this last one here. And that's going to give us this result. So look right here. Our initial database table, before we split it up, was that, right? And now the result we got out was that too. So it is, in fact, this is lossless. Now, the one thing I didn't show is how we did the decomposition. So how do we do the decompositions here? So basically, here's how we did the decompositions. R1 equals project account SEK PID from R. Okay. Likewise, R2 is doing the same thing, but it's projecting on PID, name, street, and city from R. Okay. And 3, likewise, street, city, and P code. So that's how these decompositions are calculated. Is we just do the projections off of the big R, the big table, and we get these subtables here. But now notice when we get these subtables here, we can these resulting, this is the decomposition, R1, R2, and R3. We can take these and we can just natural join them back together again and get the original relation. Okay? So doing the decomposition this way, R1 then, with these projections, is what's called lossless. Right? So does everybody, I mean, now that doesn't have to be, watch this. Let me say I do a different decomposition. So we're talking about, so this is the big table here. Let me do the following decomposition. R1 equals SEK PID name, and then R2 equals, that's over R, and R2 is going to be equal street, city, P code over R. Okay? I'm sorry, account number as well. So this one's going to get the account. It's going to, this is basically going to give us account, SDK, PID, and name. And this right here is going to give us the street. So it's basically what we're doing is we're just ripping the thing apart, based on here. So this is where R1 is coming from. This, it's this guy, and then R2 is coming from there. And then it's kind of like a triviality here. But when we take these two, R1 and R2, these ones right here, and we say, does R1 natural join R2 equal R? For all possible states. And the answer is absolutely not. Because what that'll just do is they'll just do a Cartesian, since there's no attribute to join on, it's going to do a Cartesian product, and we're going to wind up getting like 9 tuples. So it's going to be this giant, it's when we try to put it back together again, it's going to be bloated with a lot of spurious tuples in it. So this particular decomposition here is lossy. This is lossy, and this is lossless. All right. So now how many possible decompositions are there? I mean, it's a combinatorial number, right? We could probably work out, that's not really relevant. We could work out, like, given the number of attributes, how many different possible ways are there to decompose, right? So if I have 10 attributes, I start with like there's the obvious, I mean, well, you can call it some kind of combinatorial. If I have 3 attributes, I could do one decomposition where I just project on each attribute, 3 of them, and then join them together. That wouldn't make any sense. And then I can do all the possible combinations, project the 2. So there's really a very, very large number. It's definitely like some kind of factorial number of potentially different decompositions of a given relation. All right, does that make sense? I hope. Just what a decomposition is, and then what it means for them to be lossy or lossless. All right. So let's see. So now we're going to go back to this. So for some reason, we're going to have a theory later that's going to show us how to actually get this decomposition here. So that's the whole point of normalization theory, is that we have a principled way to compute what is the proper decomposition. Okay, so you don't just kind of pull them out of the hat, but there are that many of them. But what we'll see is we're going to develop algorithms to give us the right decomposition. All right. Okay. But anyways, what is this? Is this decomposition any good? Is this a good decomposition for us in any way? Let's see. Does it help us? Does it help us with our anomalies? Right. So there's less redundancy now. So if I'm going to change Mike's address now, right? Because I was changing it to Järnvägen in Stockholm. I just go to this table here, and I make the change here, right? And then any record of living at that old address is gone, right? So there's only one place. So I don't have this update anomaly where I have to update a series of tuples. I just have to go in and update one tuple now, all right? Likewise, can we delete account number 2 without deleting information on Sam? Sure. Here's Sam. All I do, so we have the information of Sam living at this address, and all I do now is I just go up here and I just get rid of that tuple there. So I was able to now handle the deletion anomaly because I just delete the account information here, but Sam, we still have address information for Sam, right? Okay, good. Anything else? Can we add information on Susie without giving her an account? Sure. We just go down here to right here, and we could add information about Susie, give her account, give her PID22 Susie. Let's put her at some, State Street. Let's call that Umeo or something. All right, so we can add that. Now we have to add that also in here to get the State Street. We want it Umeo 90751 or something. Okay, whatever it might be. But the idea here then is that we add the information here, but we don't have to add any information about Susie's account yet, right? We were able just to add in address information, and we've done it in 2 places here. But we don't have to. We don't have to do it. We don't have to have null values here. We just don't have a tuple here. Okay, there's a question here. If the address is changed in R3, right here, yeah. So here's the thing about that. Let's. I don't want to get too into that right now. But basically, the way this would be designed is that you would have a foreign key here, going from the street city to street city here. So what is in this right here? What is the key of this table here? The key is going to be street city here, and this will wind up being a foreign key into that. Okay. So if you make a change here, and if you're doing this depending on how you set the policies, it'll propagate the changes back. But that has more to do with how we implement it. But it's a good question though, just to notice that this is kind of interacting with the foreign key issue. But we'll come to that later. Okay. So anyways, I think that at least it looks like that looks like it's working well. And then the question is this now. So we had these original functional dependencies. So here are the 3 tables we have in the decomposition. And then we have these functional dependencies that we wanted to have preserved. And the question is are all of them preserved? So in other words, can we make sure that we can't, like, remember I was showing that example that I think that the name was Dave, and Dave came in and he was trying to take account number 2, but that's already been taken, right? I mean, it's already has an owner. So the issue then is that this account determines the amount and the person ID who owns it. If you put in like account number 2 here and something else, then you can basically maintain or basically this functional dependency here, you can preserve it by making sure that you keep the right state of this table here, right? And likewise with this one here, this other functional dependencies. It looks like all the functional dependencies that we wanted to capture in for the database, it looks like each of them have a happy home in one of the relations of the decomposition. And by happy home, I mean they can be enforced in that table. All right. So that the database, just by doing a local enforcement in that table, we can make sure that the functional dependency is being observed over the whole database, basically. All right. And then there's another thing also that that is not immediately obvious, but it's very, very good. And that is that when you look at it, these guys right here, they wind up being the primary keys of these 3 different tables in the decomposition. All right. So not only can we enforce the functional dependencies in these 3 separate tables, but we can enforce them by just declaring primary keys. Okay. And that's really good because there's two reasons for that. One is that we don't have to do any coding now. We just basically do it inside the definition of the database. So there's no complexity, client, especially the client complexity. And then another thing is that it's extremely efficient to enforce primary key constraints. Okay. So we're able to enforce all of our functional dependencies with just simple primary key constraints if we do the decomposition this way. Right? Okay, so these seem to be some really, first of all, it was lossless. it handled these insertion, update, and deletion anomalies. And now we can enforce all the functional dependencies, and moreover, we can enforce them with primary keys. Right? Okay. So this is kind of corny here, but boy, can't we agree that each relation is in a nice form? Right. B, C, and F. B, C, and F. All right, now, this actually stands for Boyce, Codd, the two authors, normal form. Okay, but I just put this here just to kind of draw attention that this thing right here, putting things into B, C, and F is really the end all and be all. That's what you want to get to. You want to go from this big universal big table and all that, and you want to kind of, if you can, you want to push everything down into B, C, and F. Because if you do that, then you get all these wonderful properties. Okay? So this is the theory that, instead of just kind of pulling this out of thin air, this is the theory that's going to guide us. Is this B, C, and F, Boyce-Codd normal form. Okay, so I think I already covered this, but all right. So I hope that people kind of can see that there's a good reason to kind of study, to have a good understanding of this stuff, and I hope that it's motivated now, that there's something that good comes from understanding this. Yeah. So the thing is, we have a theory, this B, C, and F, to guide us. So these decompositions. You don't just kind of like randomly kind of pick decompositions. You use the theory to get to them, I think I've gone through all these examples of. All right, so here's what our theory says here. This is kind of these are the normal forms that we're going to be considering. All right, so there's the very first and original normal form is what's called first normal form, and all first normal form says, it's very, very, very simple. All first normal form says. It just simply says that, one second, just going back. It just says that each of these attribute values in a table, they're each atomic. Okay, there's no sets. So you might look at something like this. You say R, A, B, and we have 1, 2, and 1, 17. This is in first normal form because that's atomic. For each tuple, there's 2 tuples, and that is an atomic value. It's 1. That is an atomic value. It's 2, etc. Now, if I include this here, and I go 2, and I say this, 17, 3, this is not in first normal form anymore, because now I have a list here. All right, I have a list that is not atomic. Right, maybe the elements inside the list are atomic, but the whole thing itself is not atomic. So things like JSON, if you've seen JSON, these break first normal form. Okay, so things that like this are not in first normal form. Now what we'll see later, we're not going to cover it today, but we're going to see later is that this normalization theory can still actually talk to this kind of stuff. It's kind of interesting that you can still have this normalization theory can still have interesting things to say about JSON. But for the time being, we're going to just assume that everything is in first normal form. So I'll turn this back into first normal form here. I'll just give it no. Okay. So does everybody see what first normal form is? It just says that everything is atomic. All right. And databases tend to make that assumption of first normal form. Although sometimes syntactically you'll add in, there are little things that will break first normal form, but at least from a theory point of view, is that we normally typically want to have things in first normal form. All right. So Boyce-Codd normal form is this BCNF. Most of the practical anomalies are avoided. It's been around for a long time, but it's still relevant. Efficient maintenance of functional dependencies and straightforward normalization algorithm. Okay, so we're going to look at the normalization algorithm. All right, but before we get to that, we're going to now delve into some of the definitions, and this is where things are going to get a bit more basic. Okay, a relation R is in BCNF if for every non-trivial functional dependency x to y over R, x is a superkey of R. A superkey is a subset of a key. Okay. So let's start out with this because we want to make sure that we can follow along with this with the examples. All right. So typically, when you start working with this stuff, I mean, I could have like full names here. I could have like, this is per phone number, this is name, this is address, this is email or something like this. But when we start out with something like this, we're just going to do it kind of abstractly with A, B, and C, and D, and E. All of these initial letters of the alphabet always stand for a single attribute. X stands for set of attributes, Y, and Z. All right, and then if we need to, absolutely W. Those are always representing sets of attributes. All right. So what's a key? All right. So if a key, or what is going to wind up being called a candidate key of a relation, is those attributes that are functionally, that basically those attributes which will functionally determine all the other attributes in the relation. Okay, so let's see here. All right, so let's just start out with this here. Okay, so I want to say, so there's kind of the notion of what's a key. Okay, a key, but let's not use that term. When we talk keys here, we're going to be talking two different types of keys. We're going to talk about a candidate key, and we're going to talk about a super key. These are the two terminologies that we're going to be using. Okay, so in the theory side, we're going to. All right, now, what are the functional dependencies that are holding over this table here? Okay, I'm telling you right now. So F. A lot of times I'll have a capital F like this, and I'll try to go like that to make it so it's not one of these attributes as the term. You know, I'll put an F here. F is an attribute there. F now is a set of functional dependencies. Okay, it's null. It's an empty set. Okay, so is there a super key of this relation? That is there a set of attributes that if all those attributes, we pick values for all those attributes, it will determine all the other attributes? Now there's the trivial one, and there's the basically, here's a super key. Sorry, I missed out E there. So if I give you a tuple that has a value, if I give you a value for A, B, C, D, and F, does that determine? Well, of course, that will then determine. There's no other attributes, so that would basically determine all the attributes of the tuple, right? Because it's a triviality. All right, let's this is not starting out so well, but let's do. I just want to make sure what I'm starting out here with is pretty. This is not trick. This is really easy. Let's start out with something really simple here. Okay, now F equals A determines B. Okay, so we have the functional dependency A determines B is occurring over R here. Okay, so now I want to ask is that what is a super key of this? Give me a super key of this table here. Now, remember this: is if I ever give you a table and I say, give me a super key and give it to me quick. All right, and I don't want you'll always say this. You'll always say, okay, super key is just going to be it's going to be the set of attributes where if I'm given values for each of those attribute components, I can determine all the other attributes in the relation. Okay, so if someone says, quick, give me a super key, you would say, AB. Because those are the attributes that are of the relation, right? Okay. Now the other question is this also? That's one of the super keys. That's the super keys. Okay, there's sets of set. There's a set. Is it also the case that just A forms a superkey of this relation when it's governed by this functional dependency? Well, by the definition of the functional dependency, if I give you the component A sub 1, then I can determine whatever the B component is. All right. All right. So basically, if I give you an A sub 1, I can then determine what is going to be B sub 1, maybe. That would be an example there, potentially. Let's see here. How do I say this? The relation is guided by this function dependency here, right? So if I give you a value for A, that should then determine a value for B, right? And then there's only those are only the two attributes in there. Thus, just A is indeed a superkey of this relation, right? I hope this is making sense. I mean, this is not trick. I mean, do people feel like they know what a superkey is? All right, so let's take our break now, but let's, in the middle of the break, or during the break, let's see here. Maybe we'll come back, just have so people can have something. All right, here's an A, B, C, D. A goes to B, B goes to C. All right. So my question to everybody is, what are the full set of superkeys of this relation here? And it's going to be a set of sets, right? I can already tell you one that's in that. I can start it out for you guys. Here's the beginning. We know it. Because like I said before, if someone says, give me a superkey, and they have a gun they're holding a gun to your head, if they give you a relation, it's functional dependencies, and someone's holding a gun to your head and says, quick, what's a superkey? You always just tell them all the attributes in the relation, because that's always going to be a superkey. Okay? But there are more. And then I guess during the break, people should kind of try to I give you as a yeah, well, you don't have to do it, but if you want to, you can consider this over the period of the break, is what are the other superkeys of this relation. I can tell you something that is not a superkey of this relation, and that would be just little baby d. Because if I get little d here, can I determine all the other attributes of the relation? So if I give you, so it's like saying this. It's like saying if this stood for Pershon number, this stood for name, or this Pershon number, this is email, and this is name, and this right here is the D winds up being like the color of your hair. Just given color of your hair, just given brown, can I determine who you are? Can I determine all the other attributes? That is, what is your Pershon number? What is your email? And what was your, I forgot what I had for this. Anyways. No, this is not a superkey, right? That doesn't work because I can't just go from hair color. If this was hair color, I guess what I had this like hair color. Oops, sorry. That was hair color, and then I had this as the ID, Pershon number, pnum. B here was email, and this right here was address. So if I give you the hair color brown, can I tell I say I have a person that have a hair color of brown? Can I tell what their Pershon number is? No. If I give an email, can I tell what the Pershon number is? Yeah, okay, fine. So B goes to A. Sorry, so we're now around. So B goes to A. We're going to include that one because given an email, we can determine a Pershon number. So I give somebody's email. So I have this particular email address, right? Can I determine from that, can I determine a person number? Yes. And then from that, can I determine an address? Yes. And from that, can I determine the hair color? Yes. I've been able to determine from just the email here, I've been able to determine all the other attributes. Huh. Does that mean then that, is that possible then that email is a super key? I think so. Okay. All right. Now let's get back at 1120. So there's one of the super keys. There's more of them though. So I want us to kind of grind out all the super keys. So I hope this example, this will kind of build some intuition over what this stuff is meaning. All right. So yeah. So I'm gonna just stop recording now, and then we're gonna go back. I'm sorry. Then just come back at 20 after, and we'll resume. All right. So. So did does anybody have, just maybe type in the chat, does anybody have an idea, maybe propose another super key? Anything else? Is there any other super key? Well, again, a super key means that if I give you, if you're given values for all the attributes in the super key, then you can determine the values and the remaining attributes of the relation. So there was one AD. Okay, so let's see. If I'm given AD, so if I give it AD, I can get B, right? And then with B, I can get C. So yeah, that would do it. So that would be like, that would be a super key as well. AD would be a super key. Yeah, what about A, just A? So if I have A, then I can get B, that's fine. And then with B, I can get C. And then with A, I can get D. So that would give me all of them as well. So that's also a super key. Yeah, very good. Let's see, are there any other super keys? ABC, yeah, let's see. So A, B, C. Yeah, because if I have A, I can get D. Yeah, that's another one. Are there any other super keys? So this is kind of a bit, you know, BC, does that work? I think so. So BC, yeah, because with B I can get A, and then if I with B I can get A, then I would have ABC, and I already know that's a super key, so that would work as well. Are there any other super keys? AD. I think there are. AC, yeah, I think AC is one. Any other? I think there might be one more. One, two, three, four, five, six, seven. ACD, yeah. Any more? I think it's like, well, let's say BD. ABD. Yeah, ABD. All right. So how many? So the thing is, it just yeah. Okay. I think every combination with A and B would be a super key. So every combination with A would be a super key, and every combination with B would be a super key. So you would need A and B, it feels, to get. Well, you need either A or B to get all the rest of them. Just to kind of like some kind of basic things, we have 4 attributes here. How many potential supersets do we have? How many different potential subsets are there? If we have 4 attributes, we have n attributes. How many potential supersets? How many different potential superkeys are there? 2 to the n. So there actually are going to be 16 possible combinations here because it's all the possible sets. Yeah. Okay. 1, 2, 3, 4, 5, 6, 7. Oh, well, we've got a bunch of them. So anyway, so this, I mean, very rarely, or you know, I'll never give you like, I'll never say like this, like, yeah, 10 attributes and say, give me all the super keys, because you could potentially be looking at potentially 1,024 possible combinations. So it would be kind of a miserable kind of question to ask. But even with 4, it's kind of a little bit getting a little bit out of control. So these are what super keys are. So I hope that you guys have a good firm notion or sense of that definitional sense of what a super key is. Now there's a next question, of course, that'll come up in this, and that is basically what is a candidate key? A candidate key. A candidate key is simply a minimal super key. So it's a super key, so it has to be in the super key property, and it's also super key, and also any of its subsets are not super keys. So you can't take anything away from it. If you take anything away from it, then it's no longer a super key. All right. So is ABD or ABC, is that a candidate key? It is a super key, but it's not a candidate key, because you could simply take away. We didn't have AB. AB is because you could take away C from it, and that you would still have a super key. So it has to be a minimal super key. That's what a candidate key is. Okay. So what are the candidate keys of this table here? Now give me what's a candidate key? Yeah, good. So A is a candidate key, and B is a candidate key, and I believe that's all there is. Okay, so those are the 2 candidate keys. We'll continue here. Let's see here, just so that we kind of now if I say R is A, B, C, so I say A, let's say A winds up being persona number, B is name, and C represents a ice cream flavor. And a tuple just says that person is eating that ice cream. So there's actually a many-to-many relationship here between ice cream and persona. It's like something weird's going on with. All right, so let's see. I have a person number. I have name, and I have ice cream type. So the ice cream type could be something like Ben and Jerry's fudge something or other. It could be the new Magnum something or other. And you could have something like, okay, Mike, 6144, blah, blah, blah. Not that old, actually. Mike, and then Magnum Classic. Okay, 6144 Mike. And then I'm going to have Ben and Jerry's peanut butter cup. That's actually pretty good. I'm hungry. Okay, so you get the idea of kind of what's being represented in this database table, right? So what are the functional dependencies that govern this table? Are there any? Are there any functional dependencies that govern this table? Persona number, name, and then ice cream. So I'm putting down like the record of the people, well, their numbers, their names, and what ice cream they're eating. And notice what person can eat more than one ice cream. Are there any functional dependencies that govern this table? Person number. That's not a functional dependency. Functional, that's what you're saying there's maybe what you're saying is that's the key, but what are the all right, you're getting close there. It looks like this was given as a candidate in the chat. This is close, but not quite. So if I grab a person number, then they had better agree on the name and the ice cream. But wait a sec, this is being violated in this particular instance, because I wanted to have the number, the name, and then, oh, this time he ate Magnum Classic, then he had Ben and Jerry's peanut butter cup, et cetera, et cetera. So so that's actually, that was very close. But what is the functional dependency that the name doesn't know? I mean, okay, this is interesting. So this AB determines C. That's not true. Aha, there we are. Okay, looks like we got it. A determines B. Well, this is true, right? Persona number determines the name, right? Does name determine persona number? No. A determines C. Now, A doesn't determine C because in this case here, I have oh, Jesus Christ. This number here and this number here, but there's two different, so A matches on this. It matches for this number here and this number here, but the B's are different. The Magnum Classic and Ben and Jerry's peanut butter cup. So A determines C is not a functional dependency. And are there any other functional dependencies that hold over this table? I mean, this one we agree, right? I mean, I assume everybody agrees that this one works, right? Okay, I'm telling you there's a bunch that hold, but you're not going to be very satisfied when you see them. Now B goes to C. No, that doesn't hold because we have Mike here and Mike here. So the name, I mean, what we're modeling here basically is the fact that I can eat a lot of different ice cream types. So Mike can eat Magnum, Mike can eat Ben and Jerry's peanut butter cup. So if C goes to AB, no, that is definitely not the case because then we have down here we have peanut butter cup, and then we have a whole new person 7711 named Ralph. And look at, so peanut butter cup does not determine the name because we have, if that did, then this would be Mike here, but it's Ralph. Are there any, but this one seems to be the one that makes sense over the table. Is there anything else is there any other functional dependencies that hold? All right, now I'm telling you there is, but you're not gonna feel very satisfied when you see these ones. What about this functional dependency? A, B, C determines C. This doesn't seem to have much nutrition. It doesn't seem to be telling us very much. Sure, if I grab a tuple that matches on the persona number, the name, and what the ice cream type they're eating, I can then determine the ice cream type they're eating. So there's a whole set of trivial FDs. As an example of a trivial FD, right? It's like, well, it's not telling us anything, right? So if we basically say X determines Y, this is always the case when Y is a subset of X. Yeah, exactly. So in the chat session there was somebody was saying, well, what about then when C determines C? Yep, that's also meets this. So these are all trivial. These are trivial functional dependencies. All right. So these ones actually these ones are actually saying something, right? This is actually specifying a constraint over the database. These ones are saying nothing. All right. Oh, sorry. So these are two examples of trivial functional dependencies. There's a lot of them. We don't want to get too caught up on them. So then we can say A, B, C. Yeah, we'll get to this. There's another interesting comment in the chat, but we'll get to that a little bit later as we develop things a little bit. But I just wanted to. So we have the notion of triviality of functional dependency. So we'll have to kind of keep our eye out for that. Okay. Oh, by the way, under this case right here, with this is the only functional dependency that really matters. All right, the other ones are just trivial. What is this? Could someone give me a candidate key of this table? What's a candidate? Okay, okay, quick, give me a super key. Good. That was very, very yeah, I like that because I told you if the gun's held to your head and you got to give a super key, then you just kind of list out all the attributes. Okay, great. All right. So A, B, C, that's a super key. Is it a candidate key? Let's see. What about is A, C? Is that a super key? Well, if I'm given, yep. If I'm given A and C, oh, A goes to B. Yeah, sure, I can get B, so I got them all, right? So I'm given like the personal number, and I'm given Magnum Classic or some ice cream type, and I can determine who it is that's gobbling at it, the name of the person who was gobbling that. All right, so that's a super key. Now, there's two. Those are super keys, and then we look at these. These are the possible next ones to check. Is A a super key? Well, I gave you a persona. No, it's not, right? And this is not either. Those are not super keys. So therefore, this guy right here, that is a candidate key. Okay. That is a candidate key. A goes to C is the candidate key. All right. So let's see here. So we've got some. So we have. I hope that's clear to people. Let's see if maybe I'll just do. I'll do a quick one here just to kind of get us so that we're on the. So that we're. Grab this one here, just so that we here. All right. So let's just to kind of make sure we're doing well here. A, B, C, D, E. All right. A goes to B, C, and then B, C goes to E, and then D, E goes to A. Okay. Is there somewhere in the universe that this applies? Is there an example in the universe where this is actually the way things work over in a meaning of these attributes? Most likely, yes. So most of the time, if you think about things, you can come up with a functional dependency. It's like you're talking about like physics or something. Like at every time, x, the object, determines time and position determine an object because no two objects can occupy the same spot at the same time. In a simple model. The thing is that a lot of times it's actually quite an interesting exercise to kind of try to map these things down to the real world. But anyways, this is just an abstract example. The question here is that can you calculate the candidate keys of this relation? Okay, you can grind it out, right? Okay, so those kind of issues are like determining what are the candidate keys of that relation. Those kind of things will be. Problems like this will be fair game to kind of give you. So if I give you a problem like this, I mean, give me a super key, all right, and then you can just list me all the attributes. But if I say give me all the candidate keys, grind it out, then I would expect that you. I mean, it wouldn't be very fun. I mean, there's going to be maybe some work, but I would assume that you guys are able to do that. All right. Okay, so now let's get back to this BCNF thing. So we're going to deal with the definition of BCNF. Okay. A relation R is in BCNF if for every non-trivial functional dependency, x goes to R, x goes to Y over R, x is a super key of R. Okay? And then I got there's a typo there. So that's the definition of BCNF. So what we want to do is we want to see if something is in BCNF now. Okay, so I'm telling you right now we have R, A, B, C. Okay, and here is the functional dependency that's working over that. Okay, so is this in BCNF? For it to be in BCNF, R is in BCNF if for every non-trivial functional dependency, that is this right here, A goes to BC, is that trivial? No, it's not trivial. I mean, you don't have it so that basically it's not like ABC goes to BC, it's A goes to BC. So it's actually telling you something. For every single one of these that's non-trivial, X is the super key of R. So this right here, this is X goes to Y. So X in this case here is equal to A, and Y is equal to BC. Is A super key of this relation? Yes, it is. Therefore, that checks for being in BC and F. All right? Are there any other non-trivial functional dependencies that hold over this table? No. Therefore, with respect to this functional dependency, this table is in BC and F. All right? Now, if I added to this, let's add another functional dependency in here. Add another one in, B goes to C. Right? So these are the functional dependencies now that hold over this right here. It could be something like, no, I mean, you can come with it. Let's not worry too much about what the real world interpretation might be, but we can come up with a real world interpretation where this is the case. Now, in this case here, is X is equal to B here. Is B, given these functional dependencies here, is B a superkey of this relation? Yeah, no, it's not. Therefore, X makes, I'm trying to make the noise thing. Reject, boink, you are not in BCNF. Sorry, little robot voice now. Not BCNF. Alert. All right, so this is bad. So if we basically, if these are the two functional dependencies that govern our system, then I look at these things and this is not in BCNF. All right, and that's bad. All right, what do we have here? Is that it? I think that A goes to B, C is the same as AB. Yes, exactly. So that's very good, very good. I'm glad that somebody saw that. So you guys are catching on here. So the thing is that this, if you look at this, these set of functional dependencies, these are equivalent to A goes to B, B goes to C. Good eye. Those are, but it still doesn't matter. I mean, it doesn't really matter because still, this, we've already said this is, this is just a little bit of a sloppy state here. So this kind of, you might say, oh, I don't like that. I wish you would kind of put your, when you write down your functional dependencies, Michael, could you please do it so they're not kind of, there's no extra clutter in them. Okay, well, we'll get to that because that's exactly one thing you're going to do with one of the algorithms later. But anyways, what we see here, though, that in any case, if we were testing over this would still not be in BCNF because B is not a superkey of this relation given these functional dependencies. All right. Okay. So yeah. So good. So that's not good. Actually, bad because it's not in BCNF. But we'll deal with that in a second. How we deal with that. So now when we look at those relations in the decomposition we had, if you go through and you test it and you kind of look at it closely, you will see that for each of the functional dependencies that were governing a particular table, I said that each one that had a happy home inside the relation. So when we look at the functional dependencies here, when we look at them, all right, this functional dependency is the one that governs this table right here. This is the only functional dependency that governs this table. Is this right here, is ACT here, given this functional dependency, is that a superkey of this relation? Yes. Therefore, this is in BCNF. BCNF, yay. PID here determines all those. Therefore, is PID a superkey given all these attributes here? Yes, BCNF. And likewise here, with street and city, is that a superkey of this relation here given this functional dependency here? Yeah, so it's in BCNF. So they all qualify, right? So these were all in BCNF. So that's one of the reasons why it was in such a nice state for us. That's why we all those anomalies were gone. Okay, so now what we're going to show is how do you actually go to BCNF? I mean, how do you actually compute this BCNF normal form? How do you go? Given an example, how do you then go and grind out the proper design, right? This BCNF design. So here's the algorithm, and this is the simple version of the algorithm. There's lots of different versions of the algorithm. There's a version of the algorithm in the book, which I think is a little bit more overly complicated. This is the one I think if you stick with this one, you'll always kind of get the right answer. So basically, the way it works is this: is you start out. So if you recall here, we started out with this big table here, right? And then we have these are the three functional dependencies. This is not showing up. Maybe. Well, so. I'll just do it maybe. In the notes, you'll be able to look. You can follow along with this, but I just want to kind of. First of all, what I want to do is I want to make this so that it's a bit more. That we can make this kind of a little bit simpler. I'm just going to basically say A, B, C, D, A, B, C, D, E, F, G, A, B, C, D, E, F, G. And then we have this, that is A, now SEC, that goes to B, C. This PID here is C. So C goes to D, E, F, right? And then EF goes to G. Okay, so this is just the abstract version of the problem we're doing, because this will be a little easier to handle. Okay, so I'm going to show you the decomposition algorithm to take this universal relation here, and then do the decomposition into BCNF. Right, that's what we're going to do here. Now let's start with the trivial. First of all, is that right there? Is A superkey of this relation? With A, can I get all the other attributes? Well, I can get B and C, and I can get. I'm sorry. I can get. One second. Weird. How did that happen? No, I'm sorry. I just kind of flaked a little bit here because I got the letters mixed up a little bit. I'm sorry. I shouldn't be looking at that one. I'm just going to be looking at this one. We're just going to take this as okay. First of all, is this, if it was just this right here? Well, no, I'm sorry. It can't just be that. First, let's consider this functional dependency right off the bat. Is A superkey of this relation? Well, with A, I can get BC. With C, I can get DEF. With EF, I can get G. So yes, it is, in fact. So this, in and of itself, this guy is not a problem. This guy is not violating BCNF. Great. Now, is C a superkey of this relation? Well, with C, I can get DEF, and then I can get G, but I don't seem to be able to go around and get A and D again. All right, so this guy is a this guy's a problem. Oh, now I see what I did wrong here. Okay, this guy's a problem. Okay, now I just want to make sure the correspondence works. Now I realize what I want. Sorry, just forget. I'll get to the point here. Okay, so now EF here, is this guy right here? Is this guy right here a super key of the of this relation here? Well, with EF, I can get G. So no, this is not. This is not. All right. Now the problem is I the way I did it in the example, and I want to keep the correspondence so that we get out, so that we don't have any troubles here. So, but I'm going to use this guy right here. This guy is a violator, and so is this guy here. But let's focus on this violator here. Normally, I would just kind of do this kind of as a rote thing. I wish I would have written this functional dependency here, but anyways, all right. So what are we going to do now? What are we going to do about that? What is the algorithm going to tell us to do? What the algorithm is going to do is that once we find a violator, we're going to use the violator to split this this relation. All right. So the split is going to happen on this piece of paper here. So I have R, A, B, C, D, E, F, G. Notice how I've gotten rid of the commas here just because it's, makes it simple. And I'm going to split with EF goes to G. Okay. Now the rules for the split are like this. Basically, when we split this guy, this right here, consider this to be X and consider that to be Y, and then can consider Z equals R. Everything up here in R. I'm sorry. Z equals the whole thing. All the attributes. All right, so I have X and I have Y. So basically what I'm going to come up with, I'm going to have R prime, which is going to be X union Y. So it's going to be E, F, G. That's going to be one of them. And then another one is going to be R double prime, which is going to wind up being, so we're going to split into R prime is going to wind up being X union Y, right? Which was X, there's X, and there's Y, so E, F, G. And then R double prime is going to wind up being X union Z minus Y, which could also just be, depending on how we do it, this could actually just, you don't need the X union there because it's already in Z. So there's another little typo there. Anyways, what that's going to wind up being is that's going to be basically being everything except for G. So that's going to be A, B, C, D, E, F. All right. Now, our original functional dependencies here, here are our original functional dependencies. Okay, so I'm going to do this kind of in a simple way here. When we look at this table here, this functional dependency here does not apply. All right, it does not live in that table. This functional dependency doesn't either. There's no C there. This one does. EF goes to G does live in that table there. So thus, this is the only functional dependency we're going to consider when we ask the question, is this in BCNF? So is this in BCNF? In other words, is EF a superkey of this relation? And the answer is yes. So this now is in BCNF. So we're done. We're done with, in this branch down here, we're done. All right, now let's go over here. So what we're going to set now is we're going to basically say, now does this guy have a happy home in this relation? Does he live in this relation? Yeah, because A, B, C, they're all there, A, B, C. Does this guy have a happy home there? C, D, E, F. Yeah, he does too. So these are both living inside of this relation here. Okay, so we're going to have to ask our question, the question here. Does A go to B, is A a superkey of this R double prime? Well, If I'm given A, I get B and C, and then with C, I get D. Yeah, so A is a superkey. So this is fine. This guy is fine. No problem. However, this guy right here is C, just little c here. Is he a superkey of this relation? The answer is no, he is not. Therefore, we need to split again, and this time we're going to do it a little bit cleaner. We need to split our double prime using this functional dependency here. Okay, so let's get it all set up here. So we got C, so we're going to use the split is going to be C goes to DEF. So X, that's what X equals, and that's what Y equals. Z equals A, B, C, D, F. Okay, now we're going to split that into two subrelations, and we'll call that R triple prime. And the first thing that R triple prime is going to have, it's going to have C, D, E, F. That's X union Y. And then the other thing, this is going to be R4 prime. It's going to have Z, which is A, B, C, D, E, F, minus D, E, F. So let's do this one. Sorry. If we set the Z here. So Z minus Y, which is, so it's going to be, so A, B, C, D, E, F minus D, E, F. So that's going to give us A, B, ABC. Is that right? Yeah. DEF. Yep, ABC. Okay. So now, now we have it. So okay, now what we do is we look at this guy right here. Just this little this. So we split into this right here. The only functional dependency that has a happy home in this guy is this functional dependency. Is C a superkey of this relation? Yes, because with C you can get the rest of them. So that guy's in BCNF. And then we go down to here, and then so this guy's checked. This guy right here, the only one that has a happy home is here, but does A, is that a superkey of this? Yes, so this checks as well. So this, and this, they're all in BCNF with respect to the functional dependencies that hold. Therefore, the total, when we just kind of harvest the leaf nodes here, we get R prime, E, F, G, and we get R double prime, I'm sorry, not double prime, triple prime, because we're harvesting the leaves here. C, D, E, F, right? R 1, 2, 3, 4 prime, which is going to wind up being A, B, C. Okay, and these right here, these R's, they correspond to R1, R2, and R3 of the decomposition we were showing in earlier. So when you do the substitution back for the for these kind of A, B, and C to the real names here back to this, then you get we basically have replicated this decomposition here, right? So what that shows you then is it shows you how you can go from this shows you how you can start out with the you can go all the way through. Now I have to find my slides. This shows you how we can go from just a set of a universal relation, a big table with a set of functional dependencies that kind of work over that table, and then we can break it down into this BCNF. And when you break it down to the BCNF, then what that means then is it means also that you can, if you can do that, if you can break it all the way down to BCNF, you can then put that into SQL, and you can get the primary keys and uniques, for that matter, to enforce your dependencies. And on that last point, let me just show something here. Let's say this. Let's say, what about this? What about R, A, B, C, D, and then A goes to B, C, D, and B goes to A, C, D. All right. So is this a BCNF? Is this in BCNF? Given these functional dependencies, yes, good, yeah, okay, because A is a super key, right? And B is a super key, so it's in BCNF, right? So what are the candidate keys? There's two candidate keys to this relation. Yeah, A or B, good, very good. So when you define this in SQL now, how are you going to define this in SQL? So the way you're going to define this in SQL is you're going to pick one of them to be primary. So you might say A is primary and B is unique. Okay, so via primary and unique inside of SQL, you have a perfect correspondence to enforcing BCNF. All right, so that's kind of an important practical aspect of what BCNF. When it kind of shows the correspondence between theory and SQL. So that will, yeah, that will be helpful. All right, so so what we covered today, we just really kind of did it slowly, I hope, and I hope we got some real good intuition going about normalization theory. So next time we're going to go into this. There's a lot more to be said about normalization theory. We've kind of just scratched the surface here. So in the next lecture, we're going to go into deeper issues. We're going to go into something called third normal form, and then we're going to talk a little bit about what are called multi-value dependencies. And we're going to look at the algorithm that can take us to this third normal form, and then we're going to kind of do a set of miscellaneous things, just to kind of round out our full knowledge, or round out the knowledge that we're presenting in this course about normalization theory. But hopefully that's a good intuitive start to the whole process. Yeah, okay. So if there are any questions, put them in the chat, or voice them. I'm gonna stop the recording pretty soon here. But if there's any questions, we'll stop here at this point. So. Okay. Okay, very good. I'll post this up to the non-listed YouTube film. Well, I mean, you're linkable from Canberra. So. All right, talk to you guys later. So stop.